talk. Carson's going to be giving this one. So let's start it off with a round of applause.
Make sure it's in the record. There it is. All right, I can tell now. It is on. All right, so thank you everybody for coming. If you are here for have half the service mesh with half the mess. Try to say that 10 times fast. In fact, I think going forward, I'm truly tempted to have the titles of all my talks be tongue twisters. Because if I get it right, maybe you're impressed. If I get it wrong, then I'm humanized. And so I don't know how I can lose doing that. My name is Carson Anderson. I work for Weave, not that Weave, and I'll get to that in a second. At Weave, I'm a principal engineer. That's the official title. But I prefer my made-up title of DevXO. DevX for the developer experience team that I'm on, and XO because I'm the executive officer. I consider myself the executive officer, the person in charge of making it so, the person in charge of getting it done for the developers at Weave. And that's where kind of all of this experience comes from and my main motivation for this and the things that I build for our developers. So let's get into it. Speaking of Weave, I just bring up a slide to say thank you, Weave, for letting me speak. And also, it's not the Weave, it's not the cloud native Weave. They're now defunct. We're a different company. We're an end user. None of the things I'm going to show you are a product pitch. I just want to talk about problems and solutions and share the things that we've done and kind of get your brain juices going on solving problems. Speaking of problems, let's talk about the problem I want to solve today and show you how to do that a couple different ways. So here's a very, very simple diagram of the problem. There's two problems in this diagram. I have a client. We're going to write the client today, and I want it to talk to this nebulous idea of service. And I want that client to have one problem of service discovery. Right? I don't want it to have to know even a DNS name, if I can avoid it, of where the service lives. I just want it to talk to service. I also want this second problem of customized routing. I want to be able to, on the fly, distribute load. If you're here for the previous talk, one of the things you have to do is start spreading load around, and I want to solve this problem. These are the two problems I want to solve today, and focus on just those problems. If you were going to solve this problem, and you're at this conference, you might immediately reach out for service mesh solutions. You'd go to the landscape page, you'd pick some of the big ones, because they're all going to solve both of those problems, and a heck of a lot more than just these two. So of course, why not just use one of the service mesh products, right? Like, there's these amazing products out there. Why wouldn't you use those to solve these problems and all the problems you might have in the future? The bottom line for me is it boils down to scale. Here's an overview of the CRDs that come with Linkerd, which is one of the top two. There's a lot of stuff in here. That's not to say they don't need these or these are wrong, but this is a lot to understand, right? These are all different types of things to create. Here's the amount of stuff you put in your cluster just to have the baseline Linkerd. Again, I only have two problems to solve. I may not want to have to understand all this. Again, probably not a problem for Linkerd, but it's a lot to understand for the two problems I'm solving. Here's Istio's CRDs, all the basic kinds of things Istio adds into your cluster, again, solving tons of problems, including my two. And here's the overhead. It runs off the screen of all the stuff that comes with Istio. Again, not dissing these products, but they're a lot. They're these big projects, these big apps. And I'm not paid to deploy applications. I'm paid to solve problems for developers. And I only have two, right? So there's a lot of stuff with Istio and Linkerd that I don't necessarily need. So, title of the talk, what do I mean by half the mesh, right? We know that those two products are full service meshes. So what do I mean by half a mesh? Well, if we do yet another service mesh diagram, there's really three kind of, in a service mesh. You've got your sidecars and your control plane. And in most service meshes, you have this wibbly-wobbly, networky stuff that I drew. That is kind of how you get all your network traffic magically through the sidecars. And that's your control plane, right? This is your traditional service mesh diagram. And that's a full mesh. So when I say half mesh, what we're going to do today, twice, is make our own little micro meshes that solve our problems by using just a sidecar and just a control plane. These are two completely different ways of solving the same problem. One's going to focus on HTTP. Sidecar is going to be for your HTTP people. The control plane is going to require gRPC, and I'll kind of show you how we do that. But again, we're going to build two micro meshes today. In summary, our full meshes, again, my problem was scale. My full meshes have all these extra resources. And our half mesh solutions today, our sidecar is going to have one. It's going to have one thing, and really mostly a ConfigMap. And that's the entire half mesh solution for the sidecar. And our control plane has 5 things. So a lot more approachable, a lot more understandable for me to solve the problem. I can look at one thing and know that's my whole configuration to solve the problem that I have. Again, I've already said a couple times, I like Linkerd. I like Istio. They're fantastic things. They are solving lots of other problems than the problems I have. But I want to kind of get people thinking that, remember, we're not paid to deploy applications or deploy products. We're paid to solve problems. And so we're going to do that twice today. Again, I'm speaking really quickly. Hopefully this thing can keep up. I have a lot of content, so hopefully you can keep with me. The plan today, We're going to very, very briefly show some test server and client code. I'm only going to show you that to show you how dumb it is. It's really the most basic client code and server code you can think of. I'm going to talk about this thing called XDS because we're going to use it in both our sidecar only and our control plane only half meshes. Again, the sidecar is going to focus on HTTP, and the control plane is going to be gRPC. So let's do our test server code. Here's the HTTP handler. You don't really have to understand Go at all. I don't want you to understand that this is it. The server is not smart. The server is the most basic HTTP server, listing on port 8080, spitting back the client, its host name, and the headers it got. Here's our gRPC handler. Again, if you don't understand gRPC, that's OK. Basically, understand that the server is also not smart. It is just a gRPC server that's going to return its host name. That's all we have. This stuff I'm showing you today would work with really any HTTP or gRPC client. I'm just showing you that the simplest ones will still work. Here's our test client code we're going to deploy. Again, nothing interesting here. In fact, this client is so dumb, it is hard-coded to talk to service.local and port 8080. It is unconfigurable. You can't even tell it where the service lives, because we're going to let the mesh do all that work. Every half second, the client's going to connect to the service at this fixed name and just print back what it got from the server. Same thing with gRPC. Hard-coded of the destination. The client's really dumb. It's going to talk to our gRPC server. We're going to let the mesh do the work and return the host name that it got. So that's our server and client code we're going to use for both of the demos done. I'm going to focus a little bit on XDS fundamentals because this is really important stuff, and we're going to use it in both of the demonstrations coming up. What is XDS? I used to think it was stood for Extensible Discovery Service. I couldn't quite tell what that X was, but it turns out it's all these things, RDS, CDS, EDS, LDS. I'll tell you what those are in a second. But you replace the first letter with the lowercase x as a variable, and you've got Discovery Service. Like that's what XDS stands for. This is something built and managed by the Envoy team. I'm going to lean a lot on a lot of things on the Envoy team today. Again, I like these other products, and we're going to use them today to kind of solve our problem. But basically, XDS is a kind of a standardized configuration language for service meshy things you might do. Right? And we're going to use that over and over. There are only 4 things about XDS you have to understand. There's more to it than this, but there are 4 things you have to understand today. There are LDS, listeners, which are ports that you open up and you listen and receive traffic. You send listeners to routes. Routes configure based on what kind of traffic is coming in, what clusters they're going to go to. Clusters, not to be confused with Kubernetes clusters, are just collections of endpoints of where you might, or places where you might receive traffic. Endpoints are the individual IP addresses or locations where you actually send it. So cluster is just an abstraction. So to summarize, you've got listeners that point to routes that point to clusters that have endpoints. That's the only 4 things you have to understand about XDS for the talk today. And for one of these, the first one, you only have to understand 2 of those. And that's it. So let's go ahead and get to half mesh 1, and let's actually build our sidecar only mesh using XDS files. So this is the diagram of me solving the problem today. Remember, I only had 2. And we're going to do this by having a sidecar that we run explicitly with our client. We're going to configure that sidecar with config files that we mount in from a Kubernetes config map. They're going to be live mounted so we can change them on the fly. And from there, the sidecar is going to talk to the client's going to talk to the sidecar and discover the service and go to our endpoints as we've configured it. Notice the network magic is gone. There's no wibbly wobbly stuff. We're going to do a little bit of Kubernetes work to have the client point to the sidecar automatically. So here's where we take our server code I showed you and we deploy it in Kubernetes. I show you this to show you that the server is not smart. Even the deployment is the most basic, boring Kubernetes deployment you've seen. Same thing with the beta. We have a main and a beta deploy, both having a separate set of pods in Kubernetes. Nothing interesting about these deploys. We're going to let the mesh be interesting. The one trick we have for our sidecar mesh to work is that when we create our Kubernetes services and point them at the deployment, we need to do this cluster IP none thing, where we basically say, when you hit this and resolve the DNS for this, give back all the individual IP addresses for the service instead of a load balancer. That way Envoy can do their load balancing for us. So this is the only interesting thing so far, really, about the half mesh is this one config change. Again, beta's deployed, same idea, nothing interesting there but that cluster IP. Here's our client deployment. We're finally getting to the actual part of solving the problem. Remember, I told you the network magic is gone. Basically, there's a section in our pod spec where we can tell Kubernetes, when the client tries to find service.local, which it's hard-coded to do, point it at itself, right? Because we're going to have a sidecar there, and it's going to listen on service localhost. But we do the service discovery kind of part here. We just point the client at the sidecar, and we'll configure the sidecar to match on that host name. Here's the other interesting part where we create and use an Envoy sidecar. So we're creating an Envoy container. We're mounting a config map as a volume, and Envoy is going to get all its configuration from the config files from that config map. and the client is just going to talk to localhost because of that redirect, right? So hopefully everyone's on board so far. This is the main setup for getting the client to talk to the sidecar. Now we just need to configure the sidecar. We do that with a Kubernetes config map. You're going to see a lot of walls of text today. I'm going to highlight the important parts, and I'll show you where I got all this from. It's not magic. It may seem like magic incantations, but I'll show you where it comes from. For a client, we're going to make a single file in the volume called envoy.yaml. It's going to point to a file called cds.yaml to find clusters, collections of endpoints. And we're going to point to a file called lds.yaml to find listeners, right? So those are the only two XDS things we do. We just tell Envoy, look at these files, and dynamically reload them when the directory changes. Deeper in the config map, we define cds.yaml. So lots of stuff here. Don't get overwhelmed. Basically, we're saying there's a cluster called service_main_cluster, and it points to this Kubernetes service DNS name, which, remember, is going to resolve to the individual IP addresses. So we do that for main. We do that for beta. And these are really the only non-boilerplate things in this file. It seems like a lot, but we're just making two clusters and pointing them at Kubernetes. Deeper in, we create our listeners. Again, tons of stuff here. The important part is here's where we listen on localhost. Remember, the client's coming in there. And we're going to listen on port 8080. Deeper down in the routes, we actually get to do our routing. So we say, hey, when the client tries to talk to service.local, we're going to point it to service main cluster. I'll do the kind of 50-50 split later. We'll solve the second problem. But let's just start with service discovery. Client wants to talk to service.local, we'll send you to all of the endpoints for service main cluster. Remember, the client's hard-coded, so this is where we get you could extend this to more than one service by just having different routes that match different host names, and you can build this half mesh, again, with just this one file. I know this seems like a lot, but let's take a second and look at the config. There are 167 lines of code in the client's YAML file, and most of that is the client deployment. So when I show it at you really quickly and you see all these walls of text, it seems like a lot, but let's show you a picture. This is it. I know you can't read it, but this is the whole half mesh solution. This is the entire thing you have to understand how this solution solves our problems. And if you want to change it, you change this. You don't have to go understand 20 other files or 20 different kinds of custom resources. It's completely self-contained. Also, this will work forever. This is all of the config. It's the entire control plane, if you will, contained in this one file that you have to understand. Where did that come from? Where did all that magic come from? Again, I highlighted the important parts. This all comes from the XDS specification. So if you wanted to go ahead and change the routes, you would go to the XDS API docs. You would go to something like find our route configuration. We'd go to our virtual host section, and you basically build a YAML file or a JSON file by following this very detailed documentation to fill in the gaps to solve the problems you're trying to solve. Again, you kind of have to learn this, but we're all Kubernetes developers. Like, we understand building big, kind of seemingly abstract config files to solve our problems. You understand this, you can do a lot with this pattern, and this is the entire thing you have to understand. So that being said, let's go ahead and take a second and do a demo. I'm going to go ahead and build. I've already built this, so kind of like a cooking show. Like, I've pre-baked my images. Don't worry, we don't have to watch my Go code compile. But we just built our Go code, client and server, and the control plane. And I'm going to start the demo and then show you what it's doing while it starts in the background. So we are building a brand new Kubernetes cluster using K3D. There's nothing in there. In fact, we're turning off a bunch of things to make it fast. I'm going to import my pre-built image into that cluster because I don't want to deal with registries when I'm presenting, because that's a pain in the butt. I'm going to create the clients and server YAML files that you saw earlier. So we have our services and our deployments. We have our client. It's got that sidecar. It's got the network settings. And then we're just going to tail the logs. And we're going to watch our client, again, hard-coded, automatically find our server. Right now, it's just waiting for everything to come up. So we're getting our service discovery. We're going to immediately just go to service main. And then we'll go kind of change screens and go edit the config and reconfigure our control plane with just editing a config map. So in a few seconds, again, we're waiting for everything to come up, and you'll start seeing stuff pop up here, and then I'll go to another terminal, and we'll kind of play with it some more. Hopefully. Of course, you do it constantly. All right. Waiting for it to start. OK, there we go. It's just a little impatient. So I moved to another screen just so this is faster. You notice that we have two sets of clients. We have clients 1 and 2, two sets of pods. Both of them have the same config map mounted. They found the service, and they're load balancing amongst its endpoints. So that is done. Like our half service, we've solved our problem with one config map and a sidecar. Let's reconfigure our control plane. Yeah, there's no fancy GUI here, but we can get all the things we can get from most of the service meshes by basically coming into our config map. We're going to delete this line. I'm going to change it from 100% of the time going to main to a 50-50. I know I said 95-5 in the slides, but 50-50 is better for demos. We're going to save this, not touch anything, and watch our clients reconfigure. Now, the clients do not instantly reconfigure. We've mounted a Kubernetes config map as a volume that will get live updated, but it takes a 60-second loop for the kubelets to kind of grab the new config map and remount. So on average, this part of the demo takes about 30 seconds for it to refresh. But I don't have to restart the clients. I don't have to create new pods. I don't have to change anything about the clients. I've edited the config map. The Envoy sidecar is configured to read that, detect the changes, reload, and start serving the new config instantly. So depending on how lucky I got, this is either going to take 30 seconds. There we go. So we can see one of the pods is done. The other one will come in a second. But this one right here, you can kind of see we have main and beta alternating now. We have reconfigured. We've solved our problem by just changing a config map. All our clients instantly have the new config just by changing one file in Kubernetes. So that's pretty cool. Hopefully you're kind of seeing how that's approachable. Like you can solve this, and you don't need a full mesh if you just have a problem. You can use some of the community tools to solve that problem in a self-contained, yeah, you have to understand one config file, but that's it. So tweak that config file, you get all of this stuff automatically. Well, not automatically. You can build this yourself. Again, I'm a platform engineer, so I'm really excited about tools that let me build more tools. But just change that config, and you can do all of this with this solution that I've given you. All right, question comes up. Can I just use one of these things? What you did is sort of just like a normal HTTP load balancer with more steps, right? And the answer is, yeah. Yeah, it's sort of like a normal HTTP load balancer with more steps. I just want to, again, encourage people to build solutions, not necessarily focus on deploying products. So why did I use Envoy? Well, it's built for this, first of all. It's got a lot of features. You saw that big list. That's all in Envoy. And sort of self-servingly, it's built on XDS. And we're going to use XDS again for the next half mesh that we're building. So you don't have to teach you XDS twice or some other configuration twice. But yeah, I think this is a really cool solution. You put that on the edge, and you could solve some of these problems without needing any other overhead. All right, about halfway through, we're going to focus on half mesh 2. So that was all HTTP land, and it worked with HTTP. You could make it work with gRPC and some other stuff by changing that config file. But this second half mesh is focusing really on just a control plane and gRPC. So here's the diagram of what we're going to build today. We got rid of the sidecar, and instead, we're going to use thick clients. So our clients are going to be really smart. A lot of gRPC clients, and you'll see how many, have the logic built in to talk to a control plane. They know how to speak XDS and get their configuration and obey configuration that they read from an XDS server. So we're going to solve the same problems without the sidecar and just make smart clients instead. So here's what we're going to do. We're going to write our own control plane. Yes, we're going to write our own control plane in about 13 minutes. It's not as hard as you think. I promise most of the hard work, has been done by the Envoy team. And you just need to use a smart gRPC client. And you'd be shocked at how many of the gRPC clients are smart. So Go, JavaScript, Java, all of them have full feature support for everything in XDS. And all these things with asterisks support most of the features. So even PHP, you could use this control plane, point PHP code at the control plane, and get most of the features that we're going to talk about today. So it's way more approachable than you might think. You don't have to use Go as the client. I'm using Go as the control plane because it's built for that. You might want to do that. But as the clients and servers, it can be gRPC, whatever. So seriously, are we going to write our own control plane? I thought you need an entire team. You need a big CNCF project to write a service mesh control plane. And it turns out, no. No, you can leverage this Go control plane package by the Envoy team. Again, thank you, Envoy. And build your own pretty efficiently. And this isn't just theory, by the way. We do this at Weave. We do this for hundreds and hundreds and hundreds of microservices, constant scale up, scale down, configuration change, and it works beautifully to solve our problems. Again, trying to solve problems, not deploy products. So what we're going to do is get rid of that config map and put our abstraction on services. We're going to go say, hey, I'm just going to go to my Kubernetes service, annotate it, say that this service provides our mesh service, kind of weirdly named service, and on port 9000 with a weight of 1. We'll come back to why we have a weight in a second. But basically, we configure our mesh by annotating the service to say, when a client tries to talk to service, come here on port 9000. Here's what our control plane logic looks like. It's 3 things. We create an XDS cache using that package the Envoy team has given us. We're going to watch Kubernetes services and endpoints. We're waiting and getting live updates from Kubernetes cluster about any time a service is created, updated, or changed or deleted, and all of the individual IP addresses in the endpoints behind that service change, right? So our control plane is really leaning on Envoy and leaning on Kubernetes as the data source to configure XDS. And then we're going to generate our XDS resources, very much like the YAML file from before, but with a lot of Go structs. Don't get overwhelmed when you see big walls of text. I will point out the important stuff. First thing, very easy. We pull in this control plane package, and we create this cache snapshot. This is basically a snapshot of the state of the world of all of the XDS things that I know that exist. I don't have to care about what clients care about. I don't have to care about what clients already know about. That's all handled in the cache package. I just, whenever endpoints or services change, I generate the state of the world, shove it into the cache, and the cache does the rest for the clients automatically. Again, standing on the shoulders of giants, let other people do the work and just use it. What we need to do now that we've got our cache is watch Kubernetes services endpoints. Tons of stuff here, very basic Go stuff. We create a Kubernetes Go client. We create some handlers that say every time services or endpoints change, run this update cache function. If we go deeper in the code, we see where we set up the service watcher. Again, you don't need to understand most of this. Understand we're watching Kubernetes services and keeping an in-memory index of all of the services that exist in our cluster. So it's very fast to iterate through them all because they're all just hot and ready in memory. Same thing with endpoints, the individual IP addresses behind a service. We create a cache. We watch those for updates. We'll run that update function, and we will store those endpoints in memory for later use. So we've got hot and ready all the services and endpoints in our cluster. And again, this scales really well. Like Client Go is built to scale. Every time services or endpoints change, we basically call this update cache function. In that, we use those in-memory indexes of services and endpoints to build a cache snapshot, the state of the world. We shove that state of the world at the cache, and that's it. Our clients are all able to get the updates. They know when things are added, updated, deleted. Instantly, the cache does the work for us. We just need to generate state of the world. Deeper in that get snapshot function, so every time we update, we get the snapshot. Getting a snapshot involves really a couple things. Getting our resources, so building the XDS state, sort of like that YAML, but in Go form. We're going to print it out in YAML format, so it's easier to read. I'll show you that later. And then we create a new snapshot, again, so we can shove that at the snapshot package. This is where all the hard stuff comes in. This is where the walls of text come in. Stick with me. Get resources is going to have two parts. Every single time any service or endpoint changes, we call get resources. Get resources, step one, builds a big map of all the mesh services and all of the Kubernetes services behind it, right? So we iterate over all the services in memory. We find that YAML. If it's there, we're going to parse it, and we're going to get from all the endpoints individual IPs. So we know service one provides this. Here's all the IP addresses for it. Register that with our map. So we have a big list. At the end, we have this big map of all of the mesh services and who's going to provide them. Once we've got that map, we iterate through it. And for each mesh service that we've got, we find its listener, its route, its clusters, and endpoints. Multiple clusters because we might have multiple services say they provide the same backend. So again, the same four things from before, we're just going to go over them, get all of that from in-memory, and build that same data set as before. I'm going to go through each of those four things very briefly. Get listener, again, wall of text, don't worry. You go read the docs. They're very good docs. The Go structs actually make it really easy to not get this wrong because the compiler will tell you if you have things incorrect. It's even better than the YAML. But we basically make a listener, and we point that listener at a route for a given name, right? So we have something that says, I provide service. We say, make a listener for that and point you at the route for service. Don't worry about the rest. Remember when we made routes in the YAML format before? This is the Go version of that. Again, don't be too overwhelmed. We basically say, hey, whenever someone comes into a route for this service, I want you to send them to all of the clusters that say they provide it using their weights to decide how much to distribute to each cluster. So again, using some Go code to generate that same thing as before. Remember, client's hard-coded XDS service. In here is where we put in the actual, when we see it's XDS and we go look for service, it's going to try to find it in this list of domains and then send it to the route if it matches. Remember our clusters from before? Well, here's the Go version of that. We basically go ahead and iterate through all of the individual clusters that say they provide a mesh service, and we add clusters to them in XDS. So again, we're just building up all this data of the state of the world. Moving on, we get endpoints. Getting individual endpoints is, again, going through individual providers and just slurping up all the individual IP addresses behind every cluster. We've already generated all this. This is just a bunch of Go structs that map to that YAML like we had before. That seems like a lot, lots of walls of text. When I step through them one at a time, it makes it seem worse than it is. Let's look at our slides. All right, less than 400 lines of code for the entire bulk of the control plane is in this file. Less than 400 lines of code. That's understandable. Yes, I had to build it myself, but I can grok 400 lines of code. And this is not that far off from what we use at Weave. So I'm going to go briefly here. Setting up our control plane, basic Kubernetes deployment, just running a control plane code. Our service, we're going to listen on port 18,000 for our clients, because the clients need to connect to the control plane. The clients, the only thing we do with the clients, run them in gRPC mode and give them this magic env variable. Even if your clients aren't in Go, this is the variable you give them, and you just need to tell them where the control plane lives, right? So we're going to point at that Kubernetes service, talk to the control plane here to find all your stuff. Let's run that demo. So again, actually, let me go back real quick. I got to kill the other cluster, or I won't have enough resources to run both the demos at the same time. OK, I'm going to start this. We'll scroll down, and I'll talk about the second demo. Second demo is a lot like the first. Make a brand new cluster, run our control plane, run our clients, and run our servers, just like before. Really dumb clients, really dumb servers. Less than 400 lines of control plane, not that much to solve our problem. And we're going to wait for the clients to come up the same way as before. So this will bootstrap, and we'll get into the, really I do the whole talk to get to this last part of the demo where you get to see, because we're watching Kubernetes services and endpoints, we get live updates when things happen instantly. So that delay you saw before, it's gone. We're going to see that change instantly because we're plugged right into our data source. This also would work without Kubernetes, by the way. If you have some other data source of all of the endpoints and providers and you want to build your own abstraction in a database, you could do this. You just need a list of what's the services I want to provide and where are the individual places I want to send clients when they talk to those services, right? It's all about just getting metadata. That XDS config doesn't care where the data comes from. You just need to build it. That's why I kind of built it in two parts of code. So again, step over here, tail the logs. So we have both our client 1 and 2. They're all going to service main. We're going to edit the Kubernetes service for beta. We're going to go to our annotations. And right now, the only thing providing service is the main instance. It had wait 1, remember. So when I save this as wait 1 as well, our clients instantly got that change. We have two services providing the same mesh service, equal weighted, so they get equal distribution of load, right? We instantly had that. If I were to scale up, let's add more replicas for main. It's a little hard to tell, but the clients instantly, every time the endpoints are changed, we get instant updates. Again, this is live from our Kubernetes data source because those watches are so fast that we can rebuild the entire state of the world every time anything changes. I could even go back and set this out, give that weight of 0, take it back out of load, and our clients instantly only go to main, right? How cool is that? Now I can mess with my mesh. Yeah, I don't have a fancy GUI, but this is the whole thing. I mesh with it just by editing Kubernetes resources. Again, I only have to understand that one bit of code that I wrote. Everything else is done basically by the Envoy team and the smart gRPC clients. Again, go to that documentation. It's the same stuff if you're going to do a ConfigMap or Go. The only difference is Go structs are type checked, right? But it's the exact same config because it comes from the same protobuf defs. And you can get all of these features with that less than 400 lines of code control plane by just changing the code that you generate. In fact, I was really inspired by the last talk. I want to go see if I can, when we do this kind of stuff, have our canary deploys fall back to our main deploys, because that's in here. You just have to figure out the config for it from the documentation. So we did it. I did it in less than 30 minutes. We took our full mesh sidecar and control plane, and we built a sidecar-only one focused on HTTP, where we just used one config map and a sidecar. And we did our control plane, where we built our own control plane. Again, less than 400 lines of code. That is approachable, even if you just want to do it as an experiment. You can get this code and run it. So all that said, thank you so much. My name is Carson Anderson again. If you want to run this demo, you can run this. You just need Go. You can pull it down and find all the code and go at it maybe at a slower pace at this GitHub link here. So thank you.
Thank you. Questions?
Thank you. In the first part, you were changing the behavior on the fly by updating a config map. And it's been a while since I did stuff like that, but I thought that config maps don't automatically update when you mount them as files in the deployment. You have to actually roll the deployment somehow.
Nope, that's not true. They are live mounted by default. Config maps and secrets in Kubernetes. There's a trick to it. In the way Kubernetes does it, it actually recreates the entire directory and changes the symlink. So it can be a little tricky if you're watching a file. That file handle won't get changed. So if you're using like one of the libraries for iNotify, you have to watch the root directory. So people get a little confused because they're like, well, the file didn't change. Like, no, it's still there. The symlink for the directory changed, but it is live updated.
Okay.
It's a really cool feature of Kubernetes.
Right.
Yeah, back here.
Hey, but very cool. We actually built something very similar internally to Octeto that we should have open sourced, but I'm glad now there's something there. One of the challenges we've had with our users is for non-HTTP services, queues and all those things. Do you have any thoughts on that? Like what to do for those kind of...
No, that's great. Yeah, so for non-HTTP things, in theory, and at this point, maybe I'm just building a worse service mesh, but in theory, you can take that control plane and configure your own sidecars, right? Like, if you have your own abstraction you really love that works for gRPC, XDS, you can point Envoy at the XDS server that we built in the control plane part of this presentation. And so, like, we've had that come up, and that's been my thought is if we get real desperate for that and we can't use gRPC, then I would be tempted to see how hard would it really be to just use XDS to, again, maybe I should build someone else's service mesh or use someone else's product, but if I have an abstraction I love and I can write some XDS files and send them to Envoy and have Envoy do the routing, so that's my answer. Yeah.
More questions?
Right here.
How is this different from or similar to what Istio Ambient is doing?
It's pretty much the same thing, right? So Istio, I didn't hear the second one.
No, it was just...
OK, yeah, so the other service meshes, the only difference is the lightweight version, right? So Istio, Linkerd, they do all of this and everything else, and they have fancy GUIs, but there's also a lot to understand, right? Like, if you wanted, those are full products with this giant suite of features, but if something goes wrong, do you even know where to look? Like, that's sort of my argument. With that, especially with that first half mesh, if it doesn't work, it's because your config map's wrong. That's the only thing that can be wrong, because that's the only thing you have in the system, right? So the advantage to me of something like this is that it's one file. It's also super lightweight, right? So that first example of just a sidecar and a config file, you could put that on an edge device in Kubernetes and work, and you could get the feature without the complexity. So I'm not, again, I love Istio, I love Linkerd. You just may not always need those things.
More questions? Going once, going twice. Oh,
Nope.
all right. Thank you.
All right, thanks.
We have a small